Okay, well, thank you very much to the organizers for the invitation. I'm sorry to hear that Krishnendu's not well. I hope that he's going to be with us fairly soon. Okay, so the title of this workshop is about new trends in Teichmüller theory, and it's a while since I did any research in Teichmüller space or Teichmüller theory itself. But what I want to do is I want to talk about a project that I've been working on for the last few years, which is in some sense a generalization of Teichmüller space, or generalization of one particular small aspect of Teichmüller space. So the project is about Fenchel-Nielsen coordinates. And so I've got two major goals. The first goal is that I want to tell you about this particular research project. It's quite recent research. It's currently not yet published, although most of it is in the work of my student who's already passed his PhD, so that's good. But the journals are not being so cooperative at the moment, so we're still not yet published. But the second goal is to advertise a point of view that it sort of underpins my research, and that is how to use, I'm a very simple-minded person, and I like to use very simple-minded techniques. So in the previous lecture, we heard all about how you can study Teichmüller space using Riemannian geometry and other parts of analysis. I'm not clever enough to do all of that, so I like to do simple-minded things, and my point of view is I like to use linear algebra. So whenever you hand me a surface, I like to think of that as a Fuchsian group, which I can think of as a group of matrices or of Möbius transformations, and then I can sort of deform that directly. And so this is the sort of way we're going to think about Fenchel-Nielsen coordinates. They're given geometrically, and I'm going to go through this historic construction of them. But then I'm going to very quickly turn everything into facts about linear algebra, which is a much more comfortable universe to work in. We have the geometry sitting around in the background, but by the time we get to this generalization, the geometry will have disappeared. But then eventually I'm going to come back and recover several other sorts of geometry. So here's a plan of today's talk. So I'm going to tell you about what Fenchel and Nielsen did however many years ago. It's sort of 80 years ago or so, 70 years ago, 80 years ago. And then I'm going to convert their coordinates to matrices. And these matrices are going to be to live in PSL2R, Möbius transformations, I suppose, but I'm thinking of them as matrices. And then we're going to look at, because I'm wanting to go up into SL3C, I need to be able to have a sensible way to put SL2R into SL3C. So we're going to talk about the irreducible representation. And then I'm going to rehash what I've just done for the previous two sections, and we're going to get Fenchel-Nielsen coordinates for SO21. So that's just another, SO21 is just another incarnation of the isometry group of the hyperbolic plane, but perhaps for people who work in the Teichmüller world, it's a less familiar, perhaps that's my belief, I may be completely wrong. Okay, so that's where we're going for today. So today we're just going to be sticking with hyperbolic isometries, and then on Wednesday we'll talk about the generalization and several generalizations of it. So here's the history. So throughout both talks, sigma g is going to be a connected, closed, orientable surface without boundary, and genus G bigger than or equal to 2. We've already seen sigma G in the previous talk. So if people here are working in Teichmüller space, that's very familiar. And I'm going to let pi1 be its fundamental group. And we're going to be, so the way I like to think of Teichmüller space is to think about representations of the fundamental group of the surface. So I'm thinking of sigma g both as an abstract surface, and at some point we're going to be thinking about it as a surface with a metric on it. But I'm going to consider representations to a Lie group. Initially for today, the Lie group will be PSL2R, and then later on it'll be SO21, but then Wednesday it'll be more general Lie groups. But a general fact is that the space of such representations has got dimension 2g minus 2 times the dimension of my Lie group. So how do I think of that? Well, think about the fundamental group of a surface. It's got 2g generators, so that gives me 2g parameters. I have one relation, namely the product of all the commutators should be the identity, so I subtract 1 from that, and then I want to do everything up to conjugation, and that subtracts a further 1, so I should always get something of dimension 2g minus 2 times the dimension of my group. And the space is this the space of representations, hom from pi 1 of g up to g, and then I have to do this strange GIT quotient, because if I do the ordinary quotient, I get something that is not Hausdorff. For the purposes of today and Wednesday, we won't talk about the details of that, but it is something that you should be aware of, otherwise you will embarrass yourself in public, and you wouldn't want to do that. But really you should just think of this quotient as being quotient by conjugation. Okay, so the story starts in the 1940s, the late 1940s in Copenhagen. So Nielsen had just been invited to rebuild the maths department at Copenhagen University following the Second World War, and he invited Fenchel, who was German but had had to escape from Germany in the 30s. Briefly was in Denmark and then left, but then he invited him back to Denmark to help build the mathematics in Copenhagen in those times. And they worked together on this project, and they wrote a manuscript which was supposed to have turned into a book. And in that manuscript, they constructed these coordinates on Teichmüller space. So we don't have quite an exact date for this, because I don't think there was any dating on the manuscript. Various versions of the manuscript were floating around, and eventually it was published maybe around about 20 years ago. But that was way after both Fenchel and Nielsen were no longer with us. But sadly, before they finished this book, Nielsen died. And so the book was never published, and it just circulated as this manuscript until it was eventually published. I guess there's a slight sad coda to that story, because much later, Fenchel was writing a book on hyperbolic geometry. It's a beautiful book, and sadly, he died before it was published as well. So perhaps the moral of the story is, don't write a book. So this is what we're going to be talking about, this construction. But then much later, so in the I think 1992 is the correct date here, Kouriotis and Tan, that's Christos Kouriotis and Sir-Pierre Tan, they independently generalized Fenchel-Nielsen coordinates for Fuchsian groups. So these are subgroups in PSL2C. A separate strand was Bill Goldman was thinking about convex real projective representations, and he generalized Fenchel-Nielsen coordinates. Tengren, who's somewhere here, I can't quite see where you are, but he also worked on that, and we're going to he did a slight modification which is going to be very useful to us. So I'm using his name in brackets there. And then, along with my former postdoc, Yanis Platis, we generalize this for complex hyperbolic space. So we have a situation where we have a beautiful geometrical construction in 4 different contexts. And if you were sort of living in the, let's say the convex real projective world, and you try to move to the complex hyperbolic world, or even the quasi-Fuchsian world, it would be a little bit tricky to do so, because though the ideas are all the same, they sort of have branched off. So what I want to do is I want to think about representations to SL3C, and we're going to sit all of those previous generalizations, we're going to sit those inside SL3C, and then we're going to just do one construction of Fenchel-Nielsen coordinates once and for all. We're going to see how those, how all the previous ones fit together, and they actually fit together in an incredibly beautiful way. But we want to also check that our constructions actually really does reproduce the coordinates that were produced by in this other generalization. Yes? Yes? So everything that I can do now is for works in SL3C, because I have a good handle on how to parameterize the representations of the free group in SL3C. In principle, one could do this for SLNC, but there's one step, and on Wednesday I'll talk about how we may have a little bit of difficulty. I mean, it's not a difficult difficulty. It's just we don't quite know how to write the formulation down. And then you can also you can go into more general things. You could think of okay. So, but we're going to be thinking about 3x3 matrices most of the time. Now, when we go to SL3C, or even PSL3C acting on CP2, which is the context we're going to talk about on Wednesday a little bit, we lose lots of the beautiful geometry that was probably motivated most of us to work in this area. And so we actually need to rely on the linear algebra, but I always have like a geometrical movie going on in my head, which I'm always trying to interpret into the language of linear algebra. The main tools I'm going to be using are basically traces and eigenvalues, so things that any first-year student should know. We're going to use them in a rather nice way, at least I believe it's rather nice. Okay, so let's talk about Fenchel and Nielsen and what they were doing in the 1940s. And this is framed in terms of the geometry of a hyperbolic metric on the surface. So we've already seen in the previous talk, we've seen sigma g, we talked about hyperbolic metrics, and remember we're thinking about Teichmüller space, which is the space of hyperbolic metrics on a marked surface. So we are going to, once and for all, decompose my surface into pairs of pants. So in case you're not aware, I'm sure that most of you are. So we call these pairs of pants, which is the American word for trousers, and they should be things that have three boundary components, and then otherwise are a sphere. And there are plenty of ways to decompose my surface in such a way, and there's a nice, interesting question about moving backwards and forwards between different decompositions, but maybe I'm sure we're going to hear about the pants graph later on in the conference. But we're going to fix once and for all a way of decomposing my surface into pairs of pants, and that means there was going to be 2g minus 2 of them, and they're going to be separated by 3g minus 3 curves, and you can just do a little Euler characteristic calculation to check that's the correct number. I'm also going to do a further simplification, which is not necessary for the construction, but really helps the exposition a lot. And that is, we're going to be, whenever we have a handle here, when we're going to be closing a handle, I'm going to assume that happens within the same pair of pants. So I'm choosing a pants decomposition that looks like this. And my pairs of pants are always going to be called Y, because they basically look like a Y shape. So you can see here there's a Y with a bottom there and two things. Of course, these other ones are like a Y on their side. And my curves are always going to be called gamma. And sometimes I'm going to be careful about numbering them, and sometimes I'm not. Okay, so this is what we're going to have all the way through. So let's now think about a pair of pants. Now, I'm going to use these as like Lego blocks to build up my surface. And so we need to think about what's going to happen on this pair of pants. So we're supposed to have a hyperbolic metric on there. Whenever I have my surface, whether it be the surface of genus G or my pair of pants there, I'm going to be thinking of it as a topological entity. But then, and so these curves, alpha, beta, and gamma, they're homotopy classes of closed curves that have simple representatives. But whenever I put a metric on them, I'm always going to be assuming that that is the geodesic in the homotopy class. There is a unique geodesic because of negative curvature. And so there's going to be a little bit of ambiguity there, but we're always going to think about the geodesic in the homotopy class when we think about it as a geometrized surface, but when it's just a topological surface, it's going to simply be with the homotopy class itself. So the fundamental group of the pair of pants is a free group on two generators, but it's going to be excuse me, really useful to us to think about it as having three generators, which are the three boundary curves, and there's going to be one relation, which is that if we go all of the way around alpha, then all of the way around beta, and all the way around gamma, then you can convince yourself that if you draw that curve on the surface, then it's homotopically trivial. It sort of all shrinks down to a point around the back. And so that we have, I'm going to think about it as those three generators and that relation. And because I'm thinking of homotopy classes, I'm writing it in homotopy class notation. But now if I put a metric on it, there's a lemma. This is a simple lemma from hyperbolic geometry that any hyperbolic metric is completely determined by the lengths of the three boundary components. And the way you would do that is you would if you cut along by there's a unique perpendicular between each of the boundary components, and then that decomposes your pair of pants into two hexagons. And then the simple trigonometry on the hyperbolic right angle hexagons that tell you that they're determined exactly by three boundary lengths. And the three boundary curves, they sort of come halfway along each of the three cutting curves, and they come halfway along each of the three boundary curves. So that's a very simple and well-known lemma. This is really the first step in my construction of Fenchel-Nielsen coordinates. We're always going to have three steps. This is the first step from the geometrical point of view, and probably the easiest one. So now if I'm using Lego, I need to think about how do I glue things together. So I now want to think about these pairs of pants, and they have two ends, and I want them to glue them together in a nice way so that the metric matches up. And so the first thing you notice is that the length should be the same. Otherwise, they're not going to work. But the second thing you notice is because I want to have a nice smooth metric over that curve, and I've chosen these orientations. Maybe I should have emphasized this on the previous slide. We're choosing orientations on these boundary curves, and the way I've chosen it is the inside is always on your left. So when I do that, the two curves should have opposite orientation, and then I can nicely glue. So in order to glue, you need same length and opposite orientation. And so this was always a thing that I can remember when I was about 2 years old or 3 years old. I was always confused because if cars always drive on the left, or on the right, depending on which country you're in. If cars always drive on the left, why don't they bump into each other? Well, it's because the left coming from one orientation is different from the left on the other orientation, so my surface is always on the left on this side, so I need the opposite orientation so that my cars don't bump into each other. But there's a lot of freedom with doing this, right? So that's my second step there. And the third step is I can still move these curves around. There's no unique way to glue those together because they're just nice smooth curves. And so I can twist. And so the length is an absolute invariant. It's an invariant of the metric, but the twist is a relative invariant. And as we heard previously, we usually think of a reference surface and how we move away from that reference surface. So here you can see that's my reference surface. I've just chosen one where the seam between down the sides of the pairs of pants, they just happen to meet at the same place. And now I'm fixing the left-hand one, and then I'm twisting the other one. Hopefully my drawing indicates that you can see that I've twisted by a distance, which I'm calling t. So that's going to be a hyperbolic distance. I'm always going to be thinking of hyperbolic distances for my twist. Now that twist can be positive, which is if I'm thinking of the direction I've drawn there. It could be negative if I'm going in the opposite direction. And I can twist as many times as I like. So this is the first thing you need to think about, because I'm thinking about a surface with a marking, which it means I'm thinking about my original representation of my surface. When I twist all of the way around, that gives me a Dane twist. That's an element of the mapping class group. I get the same metric on the surface, but I have a different marking. And because I'm wanting to think about marked surfaces, doing that twist moves me to a different point in Teichmüller space. So I can twist as far as I like in the positive direction and in the negative direction, and so the t is just simply a real parameter, and any real parameter is allowed. So now I've got 2g minus 2 pairs of pants. I've now glued a whole load of them together, and so what am I left with? I'm left with a sphere with 2g boundary components. So I need to think about how I close handles. So there's two steps. There's always gluing and there's closing handles. So we do the same sort of thing. And as I say, just for the simplicity of the exposition today, I'm always going to be closing handles within the same pair of pants. So I could always have done it with different ones, but that just makes things a little more awkward. So again, we need to have alpha and beta having opposite orientation and the same length in order to glue. And I have a freedom of how to twist, just like I've drawn there. And again, the twist can be as long as I like, and it can be positive and negative. Okay, so let's put all of these together. Those were the three ingredients. The three ingredients were pairs of pants with a metric on them. The second one was how to glue, and the third one was how to twist. So gluing, and when I say glue, I should say glue and close handles, and the third one is how to twist. Okay, so let's just recall, that's my decomposition. I've got 2g minus 2 pairs of pants and 3g minus 3 simple closed curves. So to build this, it's like using Lego, as I said. Each gamma j is a boundary geodesic of 2 pairs of pants, and including there the case where I've got the 2 boundary components of the same pair of pants. They have hyperbolic length Lj, so just rather than say L of gamma j, let's call it Lj. Then the metric on the pair of pants is determined by the lengths of its 3 boundary geodesics. So in red, I'm always going to count up my numbers of parameters. So I have 2g minus 2 times 3 curves there. So these are the boundaries of all these pairs of pants, which gives me 6g minus 6 parameters, which at first sight I get very excited about because that's the dimension I'm expecting, because I want 2g minus 2 times the dimension of my degree of freedom. But then, of course, I remember that I have to glue. And so that means I have 3g minus 3 gluing equations that say that some of the lengths need to be the same. But then that difficulty is compensated for by the fact that I have a twist parameter for each of the boundary components. So the theorem of Fenchel-Nielsen says that any hyperbolic metric on sigma g, given a pants decomposition, any hyperbolic metric is given by the lengths of the pants curves, which are absolute invariants, and the and the twists around those curves, which are relative invariants. Okay? And there's this important moreover statement here, that if you have any set of 3g minus 3 positive numbers and 3g minus 3 real numbers, then there exists a metric with those lengths and twists. The lengths, of course, have to be positive. In many of the generalizations, we're going to lose this moreover statement, and what we will end up doing is construct Fenchel-Nielsen coordinates on a patch of the representation space that is larger than the corresponding geometrical space that I'm interested in, but they certainly will be good enough when I want to do calculations. So now what we want to do is we want to reinterpret this in terms of matrices. And many of the ideas in this section, they're based on joint work with Yanis Plattis. So let's use the upper half plane model of the hyperbolic plane. And I'm going to consider a Möbius transformation in PSL2R, which is an isometry of H2. And in the usual way, we can lift this to a matrix in SL2R. But of course, there's an ambiguity because I can, when I lift, because the Möbius transformation has an overall factor that I can cancel top and bottom, and that factor has to be plus or minus 1 because of the determinant condition. So when I lift, I have two choices. And so we're going to take a little bit of care over which choices we're going to make. And then I'm going to show you that actually it doesn't matter, but for the moment, we just need to keep this in our head that there could be a potential problem there. Now, fixed point, so this is my part of my mantra of how to do to use linear algebra to do geometry. So fixed points correspond to eigenvectors. And the local behavior near a fixed point corresponds to the eigenvalue. So it could be dilating, it could be contracting, it could be rotating. And the map is loxodromic if it fixes 2 points in the boundary of the hyperbolic plane. And so if alpha is my curve on my surface, which I'm thinking of the geodesic representative, then I'm going to call alpha tilde the lift to the hyperbolic plane, thinking of the tilde as being like the universal cover symbol. Alpha tilde is the geodesic, fixing the two fixed points of my loxodromic map, and then that map will translate a hyperbolic distance L alpha along this geodesic, and there's a nice relation between the trace and the hyperbolic length. Excuse me a moment. And this is excuse me, this fundamental insight between the geometry of namely the length and the trace. That's going to be one of the things that really means that all my construction works. So I have here, see, plus or minus, because this matrix is only determined up to sign, and so the trace is only determined up to sign, but the cosh of the hyperbolic length is a positive number. So now let's uniformize my pair of pants. So I take my pair of pants and I cut it along two of the seams, and I get a hyperbolic polygon, which is the union of two hyperbolic right-angled hexagons. And so we can cut, and then we can reconstruct it by gluing according to the little red marks there. So we're going to use that picture a little bit later. I've chosen so that alpha is the imaginary axis, so its corresponding map fixes 0 and infinity. That's going to help us later. And y tilde is going to, well, actually, y tilde is, it should really be the whole universal cover, so I should have something called the Nielsen region, or the convex hull of the limit set. So now, remember my fundamental group of the pair of pants, I'm thinking of as a 3-generator group with one relation. namely the product of the three boundary curves should be the identity. So I'm going to think of representations of that to PSL2R. Because I'm thinking about these, I'm lifting some curves, then they're automatically going to be loxodromic or hyperbolic elements of PSL2R. And I can then lift them all to matrices in SL2R, and those matrices must still satisfy the relation, so they should satisfy the relation ABC is the identity. Right, remember though that there was an ambiguity in the lifting of A and of B, but if I choose a lifting of A and a lifting of B, that's automatically going to determine the sign of the lifting of C, because of the ABC is the identity relation. Because I'm not thinking of plus or minus the identity, I'm thinking really identity on the nodes. And so that means that even though the signs of trace of A, trace of B, and trace of C are not determined, the sign of their product is determined. And this is a really subtle point, and I've seen several people make mistakes in papers because they haven't realized this rather subtle point. So that's well defined, and this is like a paraphrase of a result of Gilman and Maskett. Now this result was actually known long time ago. I don't think anybody ever wrote it down until Gilman and Maskett do. So I say that it used to be a folklore theorem, but they really wrote it down and they did it properly. And so I'm going to attribute it to them, but I think it was known before that if you have a pair of pants, then you always have to have the product of the traces has to be negative. You can think of it as being in a component of the representation variety that does not contain the trivial representation if you want, but really you can do this by examining cases. And therefore, if we are going to make some choices, I could always choose A, B, and C so that their traces are always minus 2 times the hyperbolic cosine of the length over 2, if I want to. Okay, so remember we have 3 steps. We need to parameterize pairs of pants. We need to work out what the conditions for gluing or closing handles, and we need to think about twisting. Right? I'm going to really hammer this mantra of the 3 steps. 3 steps to happiness. Okay, so the first step is, well, I've got a representation of my group, which is actually, you can think of as a free group on 2 generators if you want. And there's a theorem of Fricker and Vogt, which I think is from about 1880 or so. I think there's 2 papers there, but they're certainly from around about 150 years ago, not quite 150 years ago. But if you have a representation of the free group into SL2R, then that is completely determined up to conjugation by the traces of A, B, and their product. So in that case, by the trace of A, the trace of B, and the trace of C. So my initial thing with the hyperbolic hexagons, that my pair of pants was determined by the 3 lengths. That is exactly equivalent in this linear algebra language to the Fricker-Vogt theorem. So that's a really nice connection. Okay, so that's my first step. I can parameterize pairs of pants, or alternatively representations of the free group, and I do that using Fricker-Vogt. Okay, so now we need to think about describing gluing. Remember, to glue the pairs of pants along, I'm going to sort of use notation here. I've got Y with boundaries alpha, beta, and gamma, Y prime with alpha prime, beta prime, and gamma prime, and I want to glue alpha along alpha prime. And I'm going to be able to lift the representations of the homotopy classes of alpha, beta, and gamma are called A, B, and C, respectively, and of alpha prime, beta prime, gamma prime, they're called A prime, B prime, and C prime. So I want to glue along alpha and alpha prime. So what was my condition? My condition was that they should have the same length and opposite orientation. So same length means they have to have the same trace, using this correspondence between length and trace. And that means that they should be in the same conjugacy class. Let's write it like that. A prime should equal and then because of the opposite orientation, then we have A inverse and not A. So the gluing conditions, same length, opposite orientation, are that A prime should be conjugate to A inverse. And because I've got a little bit of freedom of how I do this, let's just assume that A prime is equal to A inverse when I'm introducing a new pair of pants. Okay, so now how do we do that? Now this is where we need to use a little bit of very basic combinatorial group theory. I need to be able to combine these two groups. I've got two copies of a group. I want to join them together. So the usual way to do that would be to take their free product. But then we have this element, A prime is equal to A inverse, so I use free product with amalgamation. So in other words, I can write down any symbol, any string of symbols of A, B, C, A prime, B prime, C prime. Anytime I see an ABC or an A prime, B prime, C prime, I can cancel those off using the relations. And anytime I see an A prime, I can replace it with an A inverse. And then I just bring it all the way back. And so this group, actually, then you think about it, A was determined by B and C, B prime was determined, as A prime was determined by B prime and C prime. And so I end up with the free product with amalgamation is, in fact, this group here, which is now a free group on, a group on 4 generators with a single relation. And that relation comes from the fact that BC is A inverse, B prime, C prime is A prime inverse. So I get A prime times A prime inverse is the identity. And so that's where that relation comes from. Another way you could think about it is this now becomes a sphere with 4 holes, and if I go around each of the holes in turn, then the same argument that I had before shows you that curve would collapse down to the identity. So that just depends on whether you like to do things in terms of group theory or in terms of topology. Okay, we can do a similar thing to close handles. Now we need, again, we have alpha and beta need to have the same length and the opposite orientation. And so this means that B has to be conjugate to A inverse, the same argument as I had a moment ago. And so I actually need to keep the conjugating map in, so I'm going to call that conjugating map D, because that's the next letter in my alphabet, A, B, and C. And so closing the handle gives me an HNN extension. So what does that mean? It means that I take my group generated by A, B, and C, and I join a new element called D, and that element D must satisfy the relation that B is DA inverse D inverse. So what you see is that here, if I replace in my relation A, B, C is the identity, if I replace B with DA inverse D inverse, I get that the commutator of A and D times C is the identity, which is exactly the relation you would expect from here. Namely, if you go around this boundary curve, that's the same as the commutator of the curve that goes this way around, which is the A, and the D, which is the one that goes that way around. So, but the moral of this is closing a handle means you take, in your relation there, you take two group elements and you replace them with a commutator. Okay, so now we need to think about how to twist. So we've done parameterizing pairs of pants. That was Frick-Vogt. We've done gluing and closing handles. That was free product with amalgamation and H&N extension. And now we're going to see how we twist. So let's just come back to my original picture of my twisting again. So what did I do? I held the left-hand side fixed, and I moved the right-hand side by doing a translation of length T alpha along this curve here. So when I do my uniformization, then in my initial picture, I have this thing that was a union of two right-angled hexagons, which corresponded to y, and a one corresponding to y prime, and they were glued along this curve. Now what I want to do is I want to translate the y prime by a distance T alpha along this geodesic while fixing y. So what does translating a distance T alpha along here mean? Well, it means that I have a loxodromic map which has the same axis, but it has a translation length of T alpha. And I use that, in this case it would just be a dilation, and so I simply dilate the right-hand side. So I'm going to choose a map K. I don't know why I'm causing K for twist. I think it's because I'm using T for other things later on. So K is twist. And it has to have the same eigenvectors as A. That's because it had the same fixed point. It mapped this geodesic to itself. So the important thing, it has the same eigenvectors as A, and therefore also of A prime, because A prime has the same eigenvectors as A. And it has eigenvalues e to the plus or minus T alpha over 2, because that was the thing that would give me that the length would be given by the trace, this T alpha. So the trace of this map would be 2 times hyperbolic cosine T alpha over 2. Okay, so then if we twist by T alpha along gamma, it means that we pass from this free product with amalgamation to this one here, where I've now replaced I need to conjugate the second group by K, because that's what the dilation would do. I have to conjugate here, and then you might say, well, that's going to interfere with this relation in the middle, but no, it doesn't, because K commutes with A, and so I still get that A prime is the A inverse. And now my relation is turned into this. Okay. So this is perhaps a tricky step to think about when you first see it, but it's really just using very simple geometry, interpreting that in terms of linear algebra, and then in terms of group theory. Yes?
So we're thinking of gamma y, gamma prime, and groups.
Yes. 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 I'm thinking of the representation. Yeah, as Fuchsian groups. Not as abstract groups. Yes.
Okay, so actually I have a question on your previous lecture. So do we want
So here you see I've got it's the representation of the abstract group as a Fuchsian group.
Is the letter D, are we requiring it to be loxodromic?
Well, at this stage, we're just saying it's conjugate, but then as soon as we understand what's happening with the geometry, we discover it has to be loxodromic. Yeah. In fact, it's going to correspond to the curve on the torus that goes all the way around here. But yeah, it will be loxodromic. Okay, so that's doing the twisting. And now I'm going to do the same thing with closing a handle. I'm not going to go through that in such elaborate detail, but you do the same thing. This conjugating map, we replace the D with DK, and then we do the free product with amalgamation, and I get the same relation as I had here, which is again the commutator of A and DK times C. It's the same idea. Okay, so now I can put all of these together. So this is now my PSL2R, Fenchel-Nielsen coordinates. So I've got a whole bunch of free groups on two generators, which are the fundamental groups of the pairs of pants, but I'm thinking of those as Fuchsian groups. And they're generated, they get AJ, BJ, and CJ, such that the product is the identity. And I have one of those for each J between 1 and 2G minus 2. And the group is completely determined by the three traces. I'm assuming that my maps are loxodromic, and I'm also assuming that the product of the traces is negative. So that's just thinking about a subset of the space of all representations of the free group on two generators. That's the patch that I need, because that's where my pairs of pants group lives. And then I use so I get 6G minus 6 parameters because I have 3 traces, and I have for each of my copies of my each gamma j, and I have 2G minus 2 gamma j's. Now I use the Pants decomposition to glue, and to glue I need the trace to be of the two gluing things to be the same. Really, I need to be for the inverse, but so let's be strict about that. And to close a handle, I need the trace of the A and the B to be the same. So that gives me 3G minus 3 conditions. So 6G minus 6 minus 3G minus 3 leaves me with 3G minus 3 parameters. Those are my length parameters. And then when I glue, I can twist using this Kj. Now, Kj is a map that has the same eigenvectors as AJ, and then I have the parameters, the twist parameters, which come from the eigenvalues of K. And I'm going to just use a convention here, so that if I'm twisting towards, so let's actually write this down, because I didn't put it on the slide. So if I have my A, it's going to have two eigenvalues. One is bigger than 1, one is less than 1. So we can think about, so A is then conjugate to the map E to the minus E to the L alpha over 2, 0, 0, minus E to the minus L alpha over 2. And then, so that would be my A is conjugate to that. And that would mean, in this case, that K, we would have E to the plus or minus T alpha over 2, E to the minus or plus T alpha over 2. And I'm always going to assume that I've chosen my T alpha, that's the orientation on this. It would be the same as the translation of L. So I'm just going to assume that that one is a plus and that one is a minus. And you can check that if you do that from the opposite side, cars still drive on the left-hand side of the road and nobody clashes. I realize I hadn't put that. So that gives me, that completely determines my T alpha, because if I just chose the trace there, I would have a sign ambiguity, but I'm really doing it, I'm trying to be really careful about how we do this. Okay, so that gives me a total of 6G minus 6 parameters. Those are my Fenchel-Nielsen coordinates. And now let's just do a little sanity check. When I've done my gluing but no handle closing, remember that every time I did that, I got a sphere with a certain number of holes. So I've now got a sphere with 2G holes. And that's going to be given by the curves around the 3 boundary components. And then the relation is their product. It should be the identity. But then I have, whenever I close a handle, I turn a pair of generators into a commutator. And lo and behold, as if by magic, we have the usual relation for a surface group, namely that it's got 2G generators and one relation, which is a product of G commutators. So everything fits together beautifully. And when I first saw that, I thought, phew, but I also thought how nice that was. Okay, so now we're going to think about, for next time, we're going to be thinking about 3x3 matrices. So we're going to go into the parallel universe of SO21 rather than PSL2R. And so what I need to do is to work out how to pass between them, and I'm going to use the irreducible representation. Now, this treatment of the irreducible representation, it's almost the standard treatment, but I'm just going to tweak it in a very sort of way that I would like to do, because things are going to drop out nicer if I do this little tweak. So this is a tiny bit non-standard, but only a very, very tiny bit. And I'll show you where the non-standard bit comes in. So I'm going to consider the following map from R2 to R3, which is if I take a vector x1, x2, I map it to x1 squared, square root of 2, x1, x2, x2 squared, which I can call y1, y2, y3. And now, normally, people would just, for simplicity, write x1 squared, x1, x2, x2 squared. So my slight non-standard thing is I'm introducing a root 2 there and a minus sign. Now, if you observe that if we take y1, y3 plus y2 squared plus y3, y1, let's just substitute in to all of the x values, I see that that equals 0. And the reason I've chosen these root 2 and minus 1 is just to make this a nice equation, because I like that equation more than I like this equation. Okay, so what have I done? Well, y1, y3 plus y2 squared plus y3, y1, that's a quadratic form on R3. And so what I'm saying is that this y is in the null set of a particular quadratic form. Fortunately, it's an indefinite quadratic form, and so it's not that everything goes to 0. And I'm going to, this matrix here, this is the reason I like that matrix more than the one which has got some funny 1s and root 2s and minuses and things. I like that matrix because I can remember that matrix. So that's going to be my quadratic form. And so what happens is when I take my point x1, x2, I map that into R3, and I always land inside the null set of this quadratic form, which has got, yeah, you can check that it's got a signature 2, 1. If I take the vector 1, 1, 0, 1, then that would have eigenvalue +1. Minus 1, 0, 1 would have eigenvalue -1. And 0, 1, 0 has eigenvalue 1. So now what we're going to do is we now can map R2 into R3. So now I'm going to act on R2 using my matrix in SL2R. And I'm going to find it, and that turns into a linear action on R3. And that, so let's see if we can do that. So this is a real calculation. So what I'm wanting to do, I'm now putting hats on everybody in 2 by 2 matrices, because I want to reserve my capital letters for the 3 by 3 ones. Okay, so I'm going to induce an equivariant representation. So we saw equivariant representations in the last talk, but let me remind you that that means that my equivariant representation should be, if I act on I0 of x, the image under the representation should have been the same as if I take I0 and I act on the image. So depending on whether I do my action of my matrix first before my I0 or after, that gives me that's the irreducible condition. You can think of it as a commutative diagram if you want. Okay, so that's what I do. So let's do the calculation. So here I've taken my a hat and applied it to x. That gives me, that's the obvious thing from linear algebra. I'm now going to apply my IO to 0, and I get this map. I sort of then expand out the brackets and gather terms, and I discover I get this matrix here. Now that matrix is automatically going to take a vector in the null set of Q, and it's going to spit out another vector in the null set of Q. And so actually it's going to preserve my quadratic form. And so in fact it lives in SOQ. So it's an orthogonal matrix for the quadratic form Q, and it has determinant 1. You can check that. the determinant of that matrix is AD minus BC cubed. And so that's SO21. So up to change of basis, that's SO21. So I'm always going to think of this as my SO21 as being defined by the quadratic form on down here. And you also notice that if I take minus a hat and I run it through this machine, I get the same matrix out on the other side. So in fact, this was not just a map from SL2R to SO21, but from PSL2R to SO21. This is the irreducible representation that we want to think about. So let's just think about it a little bit more. So of course, ultimately, I'm going to want to think of it as sitting inside SL3C. And that's just recapping what we did on the previous slide. So using the determinant condition, we see that the trace of A is the trace of this one squared minus 1. We also notice that the trace of the inverse is still the trace of A, because it only depends on A and D. Now, if a hat has an eigenvector X with eigenvalue lambda, then a hat has an eigenvector iota of X with eigenvalue lambda squared. And that's not difficult to see. So that means that the trace of a hat, if it's equal to that, then the trace of A is equal to, well, in fact, you can just see here that the trace of A is now 2 times the translation length plus 1. And we just observe that A always has an eigenvector with eigenvalue 1. And the usual pick, maybe we can just draw this. So if I were to draw, so this is, I'm thinking about this as being the null set of Q and the inside as being a hyperbolic plane. I'm projectivizing, but if I have these 2 eigenvectors corresponding to the points on the boundary for a loxodromic map, if I take the tangent vectors, then that would give me my eigenvalue with eigenvector with eigenvalue 1. Right, so now we're ready to put all of these things together. We've got 12 minutes and 38 seconds to go, so we can put this all together, and we can develop Fenchel-Nielsen coordinates for SO21. So again, we take Y to be a pair of pants. It's pi1 of Y, its fundamental group, and we consider a representation of that. Well, we can think of it as going directly into SO21, or we can think of going via PSL2R. Doesn't really matter. But here, we just, from the previous slide, we sort of see, and all of this stuff we were doing, we see that now the traces are again given by the hyperbolic lengths. So we have the same sort of thing, something a little bit like a Fricker-Vogt thing, where this representation is not completely determined by the 3 traces anymore, because we need to have something that's analogous to this condition. And so I need this formula later, so I'm going to point this out, and then I'm going to recall it. So just put it into your memory for a moment, that if I, again, this is a little simple calculation, that if I want to look at the trace of A inverse B, well, we relate it down to the trace of the one in SL2R. And then I know that formula, so I plug that in, and I get the product of the 3 traces. Now, because we're assuming that's always negative, I'm going to take the sign changes there if I take the positive square root at this point. Okay, so that's going to be true for all pairs of pants groups. You can check easily that I choose the opposite choice of sign for the trivial representation. So that formula I'm going to recall briefly next time. So So now gluing and twisting, well, the gluing and twisting basically happens the same as it happened before. So if I glue, then I need to have my A and my A prime should be, A prime should be conjugate to A inverse, because it should have the same length and opposite orientation. And that, likewise, when we close a handle, my B should be conjugate to A inverse. And so again, I can do my free product with amalgamation and my HNN extension. All of that machinery is just going to, we're just going to roll that whole machinery out time and time and time again. So I'm not going to dwell on it. So now let's just think about what happens when we do a Fenchel-Nielsen twist. So, well, you can see what I did on the board over there. I was just sort of preempting this. So now when well, if we just come back to my, to this, you can see that if A hat is diagonal, if B and C is 0, then A is diagonal. So that's okay. So really what I've written here is I've taken the irreducible representation of this matrix and it spat out here. And I've taken the irreducible representation of this one and it spat out there. But I'm getting the diagonal matrices like that. And so, so the twist is going to be given by the eigenvalue, and I'm going to make this choice that if that value is bigger than 1, if this value is bigger than 1, then a positive twist means that this is bigger than 1. A negative twist would mean it's less than 1. So my trace, that's completely determined. If I just use traces, I would not be able to decide the sign of my Fenchel-Nielsen twist. Okay, so now we're going to put all this together. So I've got loxodromic maps A, B, C in SO21. They're determined by their traces. Well, I have this extra little thing about the square root of that from the previous slide. So I'm just going to restrict. I know what that sign should be. So let's just say that they're not only loxodromic, but they also satisfy that equation. So I'm going to get 6G minus 6 trace parameters. I've got my Pants decomposition as a recipe for how to glue. And again, just to remind you that means that gluing means that A prime should be conjugate to A inverse. So in other words, AK should be conjugate to AJ inverse. And similarly, when closing a handle, BJ should be conjugate to BJ inverse. So that's a condition on their traces. It's just a simple linear condition. And then when I glue, then I have some relative parameters, which are these eigenvalues of these maps K, who have the same eigenvectors as the corresponding AJ. And that gives me 6G minus 6 parameters. And again, that seems to be a holdover from the previous slide. Okay, so let's summarize. We've defined Fenchel-Nielsen coordinates geometrically, 3 steps: parameterize your pants, work out how to glue, work out how to twist. When I say glue, I mean glue or close handles, work out how to twist. We then interpreted those in terms of matrices in PSL2R. And then we thought about the irreducible representation, because what I really want to do is think about them in terms of SO21. But I think if I'd have just gone straight to SO21, that would have been a slight leap too far. And when I do that, I have what my 3 steps. My parameterized pairs of pants is the same as choose my traces. My work out how to glue is relations between those traces, and work out how to twist is about eigenvalues. So in the next lecture, we're going to generalize this to SL3C. We're going to go through those 3 steps, and we're going to see how that specializes in the 3 particular cases that I had in mind. That's the end of today. So I'm going to stop there, and I'm happy to have questions.
Fenchel-Nielsen result
Mhm.
with the inequality.
Yes.
How many representation, how many groups do we have in the same traces?
So,
The Fenchel-Nielsen inequality,
right.
or maybe sorry, the Teichmüller inequality,
Right, okay, yeah.
that narrows down the number of possibilities to one.
Yeah.
So like how many possibilities are we looking at?
Okay, so yeah, so the question is, with this, if I come back, I'm sorry, this is going to give you seasickness. I hate it when people do this. Right, so this Gilman-Maskit, so we have the trace A, trace B, trace C is negative. So, so the opposite choice, assuming that none of the traces is 0, the opposite choice would be the trace A, trace B, trace C is positive, and so there is one other group there. Now, of course, we have this ambiguity, and so I could always at the bottom here, if I change the sign of A, then I would have changed this one, and I would have changed that one, but they would give me the same group in PSL. One of the ways you can think about this is the following. Let me get this correct. Okay, so if I think about, this is in SL to R, if I take the trace of the commutator of A and B, this is trace squared of A plus trace squared of B plus trace squared of C minus the trace of A, the trace of B, the trace of C, and I think I want a minus 2. And that's one of the equations that you use in the Fricker-Vogt. And you can see that if I have these three traces the same, but the square is the same, but the opposite sign, then I'm picking up a new thing in the commutator here. And if you think of three hyperbolic elements, and if the trace of the commutator is 2, then that must mean that that's a trivial elementary group. So that's not so interesting. But if I have the trace as being less than 2, then we must have loxodromic elements, and their axes must intersect. So this is so. So I get the three axes, they sort of form a triangle like that. Whereas if trace of AB is bigger than 2, then there's all sorts of different cases that can arise. So that, yeah. So there's, but here, yeah, maybe the key thing is here, this group is an index 2 group in a group generated by 3 half turns, but if trace of A is bigger than 2, it's an index 2 group in a group generated by 3 reflections. And you cannot get these as a reflection group, and you cannot get the other ones as half turn groups. So there's something about this Gilman-Maskit that tells you that there's sort of 2 different flavors of geometry happening, and you need to take care of both of them slightly separately. And the pair of pants world is always in this one.
That how according to the Fenchel-Nielsen theorem, you can uniquely determine the geometry by by the length of the boundaries. So if we take the ends and the genus in account, is there some generalization to infinite type surfaces?
So say the last bit again. Sorry. That.
So if we take into account the genus and how it behaves at the ends, is there some generalization of this result for infinite type surfaces?
Oh, for infinite type surface, I see. I don't know about that. That's a really interesting question. My guess is that there will be somebody in the audience who will know how to answer that question. So perhaps we could have a discussion session at some point. I only know a tiny bit about infinite type surfaces, and there's a whole zoo of things that are quite complicated out there. So I wouldn't want to make a announcement in public. But nice question. Yes, yes. So I think, as far as I'm aware, there's essentially only one irreducible representation, and that's and all others will differ by some sort of change of basis. And I've just happened to choose my basis so that I land in a null set. I always land in a null set of a quadratic form. And I'm just choosing my basis so that the quadratic form into whose null set I land is the nice one that I like. Of course, I could have, yeah, I mean, there's a sort of entirely parallel world where I could say, well, I don't really like having this irreducible representation. Let me just embed it as a top left-hand corner of a 3x3 matrix and put zeros and a 1 in there. And that's a perfectly fine thing to do. That particular representation comes in in a very subtle way later on, but I'm going to brush that under the carpet for today. But I can maybe drop in a comment about that on Wednesday when I'm talking about it. and also, if you're doing that, you could also think about not just putting a 1 at the bottom. You could put an e to the I theta. Then obviously you have to scale everything to keep the determinant 1. And that's going to give me a component of the representation variety for SU21, which is corresponding to maximal Toledo invariant. So these are words I'm going to, I don't really want everybody to get scared by, but that is certainly there. And I will very briefly talk about Toledo invariant on Wednesday without giving any definitions.